Hi, everyone. Thanks very much for the opportunity to present today. So I'll be changing gears a little bit to talk us about a specific application focusing on icy ocean worlds in the outer solar system. So here's just a brief outline of the things that I want to cover. Taking a broader perspective, we'll do a brief introduction to the ocean worlds in our solar system. We'll also briefly cover some of the different ways that you could drive fluid flows within these bodies, and then cover some of the governing equations and common approximations that are used to simulate these worlds, and then do a slightly deeper dive into some examples of rotating convection in these bodies, and then thinking about how we can test the resulting hypotheses for these oceanographic processes with upcoming missions, and then just wrap up with some conclusions. Okay, so to start off, we at present day know that there are 4 confirmed ocean worlds beyond that of the Earth. And in the Jovian system, this includes the moon Europa, which is kind of shown in this schematic here, if I can get the laser to work right. Apparently I can't. So this is a little bit smaller than the Earth's moon. It has an outer icy shell that is thought to be something on the orders of tens of kilometers thick. Then below that, it has a roughly 100-kilometer thick ocean. And then below that, a rocky mantle and potentially a solid, or not a solid, an iron alloy core, although this is under debate. Also in the Jovian system is its larger next outward moon from Jupiter, Ganymede. And Ganymede is quite a bit larger. It's actually larger than the planet Mercury. So this also has a thick hydrosphere, but because Ganymede is so big, you could have layers of water and different variations of high pressure ices. So that's kind of shown in this schematic here, where you could have these different types of liquid and solid alternating layers with a rocky mantle below that. And there is a iron alloy core at the center, which has its own dynamo field within it. Looking for a little bit further out in the Saturnian system, we have the small moon Enceladus. So this only has a radius of 250 kilometers. It has an outermost hydrosphere, which has a global ice shell overlying a global liquid water ocean. And below that, it has a rocky, potentially porous core with hydrothermal activity. And then further out in the Saturnian system is the moon Titan. So Titan is unique because it has a thick global atmosphere, in addition to a thick hydrosphere where you have this outermost ice crust, a thick global liquid water ocean, and then potentially another layer of this high pressure ices, because Titan is also a large ocean world. And you can kind of get a sense of their sizes respectively in this schematic down here. So those are the ones that we are very confident in terms of there's multiple layers of detection for oceans. But there's also some tentative ocean worlds out in the solar system. So in the Jovian system, that includes the moon Callisto, which is the next one out beyond Ganymede. And in the Saturnian system, it's hypothesized that Mimas and Dione also have oceans beneath their outer icy crusts. And then Pluto, one of the dwarf planets even farther out, might have an ocean as well. And those are bodies that have one line of evidence that suggests an ocean. But there's also bodies where we have less data, but there has been theoretical work that suggests that there are oceans beneath their icy shells as well. So in the Saturnian system, this includes Rhea and Tethys. And then beyond Saturn and the Uranian system, there could eventually be oceans in Miranda, Ariel, Umbriel, Titania, and Oberon. And in the Neptunian system, its large moon Triton is also a potential ocean world based on these theoretical considerations. So one thing that I wanted to kind of highlight here is for all of these bodies, we have a relatively data poor understanding. So we know that oceans exist, but we don't really necessarily even know what the compositions are or how salty they are. But as a converse, that is a possibility-rich universe to take a positive spin on not knowing all of those constraints. So besides the really awesome fluid dynamics in these worlds, there's other reasons that people are really excited about exploring these bodies. And one reason is because they're really exciting prospects for habitability. And this is because both Europa and Enceladus, which are the smaller ones that have direct ocean interaction with the rocky seafloor and the ice shell above, show evidence of geologic activity, shows that they are dynamic worlds. And one of the reasons that that is significant is because if you have these oxidants that are produced on the surface that are created by radiation from either the Jovian or Saturnian magnetic fields, if that can reach the ocean, and if you have any type of hydrothermal activity down in the seafloor, if you have these reductants mixed with these oxidants, that's a potential driver for chemical energy for life. And then similarly on Ganymede and Titan, we have the similar process, but it's slightly more complicated by this presence of high predator ice layers, although you are able to have exchange across this boundary as well. So from the broader planetary science perspective, this is one reason why ocean worlds are really exciting in addition to the fun fluids. Okay, so let's kind of talk a little bit about the different ways that you can drive flows within these worlds. And one of the things that is really fun is that these, I think, are a really natural laboratory for comparing against the Earth's ocean, because there are some things that are similar and there's some things that are very different. And it allows you to test different assumptions that are made, and then you can learn about both by testing those ideas. So some of the things that are both common to the Earth and these extraterrestrial ocean worlds is that some common drivers are buoyancy-driven flows, so that's just due to density anomalies driven by temperature and composition, and then also tides. But slightly more exotic compared to like the Earth's ocean, for example, is that you could have libration, precession, and electromagnetic pumping be more significant for moons in orbit around a planet than potentially at the Earth. So to just go briefly over some of these different mechanisms, starting with buoyancy-driven flows, which I'll return to later on in the talk. But just to reiterate that this is caused by the exchange of heat and salts with the ocean, and this is going to be relating to the interchange between the seafloor and the overlying ice shell. There's a few different ways that you could drive vertical thermal convection. You could have radiogenic heating within the mantle, or you could also have tidal heating, which could be more significant, but it could also be spatially heterogeneous, as we'll talk about in a little bit later. And then you could also have this modified by there being water-rock reactions. So this could influence the salinity of the ocean, and you could also have melting and freezing that modify this ocean salinity from above. So far, those are, we've been talking about like the vertical contrast, but there could also be really significant horizontal perturbation drivers in these systems as well. For example, I mentioned tidal heating could be spatially heterogeneous, where you have much more flux coming out of the poles than at the low latitudes. But conversely, if you have large gradients in ice shell thickness, then you could have some regions of the water column along the ice-ocean interface be much cooler than in other places. So you set up this horizontal contrast there. So that could also drive horizontal convection in these systems that you would want to take into account. Okay, so I just want to briefly talk about, because we want to not only understand rotating convection, but that has to be considered in an integrative context, because when you go to these worlds, all of these different processes are going to be acting in aggregate. So in addition to these buoyancy-driven flows, we want to consider how these could be driven mechanically. So this could be due to the moons being locked tidal orbits, or locked orbits around their host planets, and this can also affect their rotation. So these tides are going to be deforming the moon, because as they are in eccentric orbits, they are going to get pulled more deformed when they are closer to the host planet, and then that deformation is going to be smaller as they are farther away. And you could also have a small oscillation between the directions of the bulge and the direct line of sight to the planet. So those are eccentricity tides, but you can also have tides due to obliquity. So that's going to be due to the offset between the orbital plane and the rotational axis of the body. So you can also have tides due to obliquity effects. In addition to that, you can also have all of the different moons in the system interact tidally as well. So once you have these gravitational tides that can form, this can also lead to tidal torques that can lead to periodic changes in the spin state of the moons as well. So you not only have the surface of the ocean deforming, but you could also have the spin state evolve as well. So to just give a couple of different flavors of the different flows that can be driven by mechanical forcings, here I'm just showing some examples calculated by Mark Rivera Navarro, looking at the barotropic response to eccentricity tides and obliquity tides, and these are solved through the tidal Laplace equations, which I'll talk about in a little bit. So the main thing to note is that you have some surface displacements for the eccentricity tides are relatively large. They are tens of meters. And then you can have flow speeds in this example of several millimeters per second. And then conversely, for obliquity tides, you have a smaller surface displacement, but you can have a much more substantial flow amplitude, where in this case, you have flows on the order of 5 centimeters per second. And this is taking Europa as an example. So in addition to driving flows within these oceans, they can also generate significant dissipation within the oceans. So here's just some examples showing the eccentricity tide dissipation as a function of how hard the ice shell is in terms of its effective rigidity. So hard ice shells are up top here, and soft ice shells are down at the bottom here. And then on the x-axis here is the Lamb parameter. So this talks about the relative perturbation of the tides compared to surface gravity waves. So the things to note here is that in these yellow colors, that's where you have regions of really intense dissipation. And then the moon values are kind of incorporated into these white dots here. Yeah.
The amplitudes in the top level, like the 20-meter surface changes, does that assume hard ice or soft ice, or does it matter?
For this case, it doesn't really matter so much in terms of, I'm thinking about Europa in particular, where if it's soft or hard, it doesn't, they're still going to be on the order of like tens of meters. Like the best estimate is like 30-meter tides for Europa. Yeah. Yeah, so they're pretty large. Yeah. So if you consider obliquity tides, here's where you can have even larger dissipation values. So here I've shown a couple examples for Triton and Europa, where they can get up to, I can't read the numbers from here, it's a little fuzzy and my eyes aren't that good, but they could be quite substantial for these two bodies. So those were relatively simplistic calculations where they took a lot of assumptions. For example, they only had the 2D response and they were linear. So if you take a slightly more complex system, considering eccentricity tides where you're now incorporating inertial waves into the system, here you can see in this example where you get these shear waves that form within the ocean where you have lots of concentration into these kind of shear zone features, and those are areas where you could have enhanced dissipation as well. All right, so those were the tides examples that I just wanted to briefly highlight. We can also consider libration examples. So this is an experiment that was conducted at UCLA by Daphne Lamosquerier, and this is just showing how you could have your rotating tank, and then in addition, you have small oscillations that occur on that. And when you have these types of librational flows, you could have the flows either be concentrated on the boundaries, or they could extend into the ocean bulk. They could be quasi-steady, or they could consist of growth collapse cycles. So there's a lot of variety of libration responses that could be identified for these ocean worlds as well. So to kind of give you an example of what these libration-driven elliptical instabilities look like for these types of moons, this is an example showing how it can lead to this space-filling turbulence. So then you might wonder, how can we apply these types of laboratory experiments to the icy ocean moons? So that's done by this figure here. So this is basically just showing the Ekman number as a function of the libration amplitude. And the thing to note here is that this gray area is where you are unstable to this type of elliptical instability. And then down in this white area is where you are stable to this elliptical instability. And these colored markers here are showing estimates for Europa's ocean, which is shown in these kind of diamond areas. And Enceladus is shown in these upside down triangles. So the thing to note is that for those two bodies, you are predicting them to fall in the unstable regime. So we think that this type of instability could be relevant, especially to Enceladus and possibly to Europa, but it's unlikely to be relevant for Titan, Callisto, and Ganymede. Okay, so there's also a third potential driver of fluid motions in these worlds, and that is electromagnetic pumping. And this is where you have the magnetic field of the host planet, say Jupiter in this case, and it has a about 10-degree tilt away from the rotation axis. So when you are the moon, you will see this periodic perturbation of the magnetic field, and then the motion of that satellite around, say Jupiter in this case, will create an induced magnetic field. Then you could have interactions between the Jovian field and this induced magnetic field, which is argued to potentially drive flows within the ocean of Europa. So in this case, they are predicted to create like a unidirectional jet in the equatorial region. And because this relies on the strength of the host planet's magnetic field, this is most relevant for Europa and less relevant for Ganymede, and it wouldn't be relevant for the Saturnian moons because Saturn's magnetic field is largely axisymmetric. Okay, so that's kind of a brief overview of the different types of ocean worlds and what we might be expecting to be happening inside their oceans. So now we'll kind of briefly shift gears to talk about the governing equations, noting that these have been covered a little bit already, but one thing I wanted to kind of highlight here is that I've tried to put together with colleagues a rather comprehensive form of the conservation of momentum where you include, for example, the variations with gravity. So you have your conservation of momentum that includes, like, say, the Poincaré term. You have the Poisson's equation to cover the perturbations with gravity, which is especially important for mechanical forcing. You have an equation of state because you want to relate the density of your fluid to deviations in the temperature, the salinity, and the pressure. You have conservation of mass. In this case, we've looked at the inelastic approximation. You need to conserve salinity when you melt or freeze in your system. You also conserve heat. And then in some cases, you want to consider magnetic induction.
Question?
Yes.
Do you have stratification effects in the oceans themselves? Are you taking that into account?
In these ones, yes, in essence, you could. But I would argue that we don't really know what the stratification is, but it's possible. And we'll talk about that a little bit more, especially in the case of Enceladus. So I gave you the governing equations, but I also think it's important to talk about common approximations that we use when we solve these problems. So the most common approximations here are the assumption of no magnetism. There are a few studies that look at the influence of magnetic fields. The vast majority of don't. And we also generally make the assumption of a Boussinesq approximation, so you don't take into account any background variations in the density field, which I think is fine for the small moons. You might talk about it a little bit more for like Ganymede or Titan where they're larger. I still think the effects will be small. And then one other point that I wanted to highlight here is that we've talked about the potential for these buoyancy-driven flows and mechanically driven flows, but the vast majority of these studies consider them independently. So you want to, like many have studied either like the convection side or the mechanical side, and that's because there's different assumptions, approximations that are made in each of these different approaches. So when you focus on convection, you are thinking about the processes that exchange heat and salinity, and this determines the stratification structure of the ocean. And conversely, when you think about mechanical drivers, this is where you kind of neglect the processes that create a stratification, and here you just assume that as a background. And then some of the most common approximations are kind of highlighted by color here. And also note for the colors that I've selected for the mechanical, these are the ones for the tidal Laplace equations. And then one other aspect that I wanted to note here is that ocean flows are likely turbulent, but when we're doing numerical models, we are not able to resolve all of these flows. So there are a few different approaches that people can take in order to deal with this issue. We can do numerical simulations where you just have the wrong Ekman and Rayleigh numbers. So you basically just neglect any effect at the smaller length scales and time scales. Or you could do large eddy simulations where you make some assumption about how the turbulence behaves and try to parameterize that into your models. Okay, so now let's go a little bit deeper into rotating convection with those examples. So as I mentioned, this is where you want to take into account the processes of radiogenic and tidal heating in the seafloor, as well as interactions with the rocky mantle that influence the salinity gradients. And then you also want to take into account how it will interact with the salinity of the system and also spatial heterogeneities on both the top and the bottom boundaries. So in the simplest case, when folks first started thinking about the dynamics of icy ocean worlds, the majority of us started with thermal convection. So that basically just assumes that you have a hot bottom and a cold top. And this has shown that you can generate hydrothermal plumes in the ocean. It can lead to turbulent convection. And it can also lead to global overturning circulations in terms of like zonal flows and even potentially like Hadley-like type cells in the ocean as well. So when we want to do these types of numerical simulations, we don't necessarily have in situ data that we can use to guide our simulations. We can rely on rotating convection theory and particular scaling laws. So what I'm showing here is just the Rayleigh number is a function of Ekman number. And then I've color-coded this according to different convective regimes. So in the gray, this is where we would have subcritical, so no flows. As you go slightly up, you're going to have this geostrophic turbulence plumes and columns type of convective regime where you have strong rotational effects. Then in this yellow region is kind of taking into account the uncertainty in where the transition between this really strong rotational influence to more rotation-affected unbalanced boundary layers occurs. So we want to take into account that there are several hypotheses in the literature for what that transition could be. So one of these is an example from Keith Julian's work, to call out Keith. And then in the red, this is going to be the transition from this kind of rotation-affected to non-rotating heat transfer. And this is where you have even more uncertainty in the convective regime. So for example, we have the convective Rossby number of 1, which will be in these dashed lines. And because that does have some Prandtl number dependence, it has two different options for a Prandtl number of 1, which is usually used in the numerical models, and a Prandtl of about 13, which is more appropriate to the icy satellites. So when we have that framework of how rotating convection behaves, we can take our best estimates for the heat flux and the ocean thickness and general parameters and make an estimate for what the Ekman and the Rayleigh number are for the known ocean worlds. So in this kind of cyan color, this is the estimates for Europa. Ganymede is in this darker blue. Titan is in this gray. And you can see they all kind of cluster together. And they seem to fall either close to the transition between an unbalanced boundary layer and non-rotating heat transfer. But because of the large uncertainty in where the most appropriate scaling law is, you could either see that it's in this unbalanced or near the non-rotating regime. Enceladus is a bit of an outlier here where it has a more solid foundation in this unbalanced boundary layer regimes. But I also have a little arrow here to signify that this is sensitive to the thermal expansion coefficient of Enceladus's ocean, which fits into our estimates for the Rayleigh number. So if you have a less salty ocean, this number is going to go down. So you could imagine that you could go more towards this geostrophic turbulence regime quite easily if you have a different ocean salinity and then therefore a thermal expansion coefficient. So we can use that to make estimates that Europa, Ganymede, and Titan are weakly to moderately constrained by rotation, while Enceladus could be strongly constrained by rotation.
Question?
Yep.
Do you have to take account of the fact that the expansion coefficient changes sign near the ice layer, so that there's kind of a penetrating convection buffer layer at the top?
You should. In this case, I have not. When there are a few studies, and I'll talk about one of them that does take that into account. Yeah. So one thing that we want to do is it's generally known that there is a strong dependence on the convective behaviors as the influence of rotation changes. So this is just a study that I did a number of years ago that has 2 swipes through parameter space here. So I'm just showing this one here where the Rayleigh number is fixed, and then we vary the Ekman number here. So as you have faster and faster rotation, you go from cases that are quite viscously dominated to ones where you have retrograde flow at the equator towards multiple jets as you get to stronger rotational influence. We can also consider the radial flows here. So in the kind of the least rotationally constrained case, you have more isotropic behaviors as you would expect, so you don't have any preferred orientations. And then as you increase the influence of rotation, you start to have an upwelling of warm fluid at the low latitude regions. And that starts to break down as you get to more and more rotational constraints where you really have that axialization of the fluid flows. And then this could be looked at in terms of the implications for heat flux along the top boundary of the simulations, where if you have any spatial heterogeneities in the heat flux coming out of the ocean, that could manifest itself into ice shelf thickness variations that could potentially be observable by spacecraft. So here I'm showing latitude as heat flux as a function of latitude here, where in the least constrained case, you have something that's relatively flat, as you would expect. And then the more moderate, weakly rotationally constrained cases, you have this pulse of equatorial heat flux due to this upwelling of fluid, but you still have a secondary peaks at higher latitudes. And in this more rotationally constrained regime, you have peak flux coming out of the ocean at high latitudes. So you see this distinction in patterns of heat transfer as the rotational influence is changed. And you see a similar trend if you instead go down in this parameter space instead of across. Okay, so as I mentioned, there is the possibility that the heat flux along the base of the ocean, the seafloor, is potentially not uniform. We would expect it to be uniform if the mantle heat flow was dominated by radiogenic heating, but it could also be significantly impacted by tidal heating in the mantle. So in this case, you would expect there to be a lot more heat flow coming out of high latitudes than at the equator, and you would also have some longitudinal variations that are taken into account there. Okay, so these are some work that Daphne Lamasquerier ran when she was at UT. So here I'm just going to show you what happens if you assume radiogenic heating. So this is going to have a uniform heat flux along the seafloor with stress-free boundary conditions. So this is essentially one of the cases that you just saw in the previous study, where you have this 3-jet zonal structure, and then you have this upwelling of fluid flows. So if you then instead consider tidal heating being the predominant heat source along the seafloor, here's what you get instead. You still have this equatorial upwelling in terms of the radial velocities, and you still have this 3-jet zonal flow. It gets a little bit more interesting if you also consider no-slip boundary conditions. So it's been argued that no-slip boundary conditions might be more appropriate for the ocean worlds, but we consider both because there is the idea that you're already at too high of Ekman, so you might minimize your effects of viscosity by incorporating the stress-free boundary conditions. So in this case, you have something similar where you have more of your radial motions concentrated at low latitudes, but you have quite a different characteristic structure of your zonal flows, where you now have prograde flow at high latitudes, equatorial region, and at in the South Pole as well. Where it gets really interesting is when you consider the tidal dissipation pattern along the seafloor with the no-slip boundary conditions. So in this case, you see not too much difference in the radial flows, but you see quite a dramatic change in the zonal flows here, where you, instead of having this really axisymmetric zonal flow, you instead have thermal winds that can develop in this case. So because we're also interested in the heat flux pattern, we've looked at the heat flux pattern. This is the non-dimensional normalized version of the heat flux as a function of latitude. The dashed lines is the heat flux pattern along the seafloor that's imposed. And then the solid line is going to show you the value at the ice-ocean interface. And the black colors are for the uniform seafloor. And then as the color becomes more and more yellow, you're going to have a larger contribution by this tidal heating component. And the thing to notice is that in both stress-free and in the no-slip boundary conditions, you see a mapping of that seafloor heat flux pattern to the ice-ocean interface. And that's especially represented by this plot here that compares the heat flux at high and low latitudes for the top and the bottom. And if you follow this black line here, that is going to be like a one-to-one mapping. And you can see that for both the stress-free and the no-slip conditions, we have an efficiency of this heat transfer at about 75%. And I'll just note that even though this is shown for like 1 Ekman number. This also holds as you go towards lower Ekman numbers. So it seems to be a robust finding that if you have this latitudinal heat transfer variation that is effectively mapped to the ice-ocean interface, assuming it's this large-scale phenomena. Okay, so we've also had some questions about the potential for stratification. So one thing that you have to take into account, especially for small ocean worlds, especially Enceladus, but also Europa, is that the salinity and the pressure can affect the thermal expansion coefficient of your water. So the thing to note here is that in the red colors, this is where your thermal expansion coefficient is positive. So that's where water behaves as you would expect, where if it's colder, it's more dense and it would sink. But conversely, where it's blue, this is where the thermal expansion coefficient becomes negative. So in this case, when it gets colder, it actually becomes less dense. This is especially relevant for both the top and potentially the bottom of the ocean of Enceladus. One thing that this can then lead to is that you have the potential for there to be a stably stratified layer at the top of these oceans that could potentially separate the convective layer from the ice-ocean interface. So there was some nice simulations run by Zhang and Janssen where they have, for example, considered the injection of particles, say at mid-latitudes as compared to high latitudes. This is considering a low salinity case where you can see these materials kind of transport up. And this is the case where it's just uniform, so then they just stop where they kind of reach this stratified layer ceiling and they don't penetrate it very quickly. And conversely, if you have it more concentrated near one of the poles, you can see a less diffused, it takes longer to have that material go. So you're really limited to one hemisphere if it's more located near the pole. Yeah.
I don't remember if you said this earlier, but are there constraints on the salinity of the oceans? Because like if it was greater than 20, and I don't remember what the units are, then this didn't seem to be in effect.
Yeah, so for Enceladus, we have some constraints through a number of different sources. So one of the things about Enceladus, which I forgot to mention, is that it has plumes of liquid water that are ejecting from its south pole. So we were able to get estimates of what the ocean might be made of by sampling those plume materials. Granted, that has this huge assumption of this is what we have measured in space, and it has to get through the entire ice shell, so that could modify. So there is some estimates, and I think that this range is quite relevant to Enceladus in terms of the bounds that are possible. But then one other thing that comes into play in terms of the stratified layer is that if you have material that's being ejected, it could be sampling from this stratified layer, which could be different from this convective layer. So even what you have measured from the plumes might not necessarily be representative of the whole ocean. Yeah. Cool, thanks. Okay, so one other thing that you want to take into account is that you could potentially have variations of ocean salinity as a function of depth as well. So in this case, you could have both gradients in temperature and in salinity across the ocean depth. In this case, you would then have to worry about double diffusive convection because heat and salinity diffuse at different rates, with the salinity diffusing much more slowly than the temperature. So there was a set of simulations carried out by Teresa Wong a couple of years ago. So in this case, they have assumed more stratified, uniform temperature profile, and then a compositional profile where it is less dense at the top and more dense at the bottom. And in this, they then ran this simulation, and you can see that this forms initially 2 layers and eventually forms like this staircase structure where you have these really defined layers and sharp gradients in the temperature and the compositional fields. But eventually these staircases start to merge, and then you have mixing across the ocean. So this is another possibility that we would want to consider as being relevant for these bodies, with the question of like what time scale would this occur on. And this also has big implications for habitability and the exchange of materials from the seafloor and the ice shell. So speaking of the ice shell, for Enceladus, we also have been able to make maps of the ice shell thickness variations from the Cassini spacecraft. So here's just a couple of examples. This is the largest scale topography, where the thing to note here is that you have thicker ice at low latitudes, thinnest ice near the South Pole. It could be as thin as like 5 kilometers here, as opposed to something more like 30 at the equatorial regions, and then you have an intermediate thickness near the North Pole. So you can take these estimates of ice shell thickness variations, and then this may also then have the consequence of overturning circulations within the oceans themselves. So there's been a couple of studies that have looked at this, and here I'm just going to show one example from Wan-Ying Kang. So she has considered a couple of different possibilities for the fresh ocean or a salty ocean, because both of those are potentially significant for Enceladus's ocean. And the thing to note here is that the equator, the ice is relatively thick, and in this case, you're going to have cold ocean water just because of the change in the pressure-induced melting temperature, so that's going to cause a difference in the temperature, the top of the ocean between the different poles and equatorial regions. Then you're also assuming a steady state in terms of the ice shell thickness, so in this case, you're going to have freezing and melting occurring here. So when you freeze, you are going to reject salt. So you're going to have, you reject salt, you're going to have saltier water, as opposed to where you are melting, you'll have an injection of fresher water. So in the fresh ocean case, you could then have this overturning ocean circulation that goes from the warm fresh towards the cold salty, and then you'll have the transfer of heat and fresh water towards the equatorial regions. And then for different reasons, in the salty ocean case, you still get this preferential transport of heat and fresh water towards the low latitudes, where you instead, even though you have this different direction of ocean circulation, you have it offset through diffusion at the poles. So that's one advantage of being able to have measurements of what the ice shell thickness is, that you can use that to kind of constrain what the ocean circulation might be. Taking the opposite approach in terms of like looking for the heat flux pattern, which could then explain the observations. And then there was a new paper that John had mentioned recently, or this morning, by Gastine and Favier, where they use a new field phase approach where they've looked at thermal convection in a model that is able to incorporate both a liquid component and a solid component in a single model, where they're able to incorporate the effects of melting in the ocean circulation. So this is just a figure kind of illustrating that. This RM is showing you where the phase boundary is, and then these two different temperature colors are representing the ice and the ocean. So I think this is a really exciting direction for future modeling work. And one thing that they find in their study is that as the influence of rotation increases, then you have a difference in terms of the axisymmetric ice shell thickness is going to go from being relatively thin at the poles towards being relatively thin at the equator. So that's going to also change with the rotational influence, in addition to be kind of locking some of the oceanographic structures with the topography of the ice shell that John had mentioned earlier. Okay, so the last thing I kind of wanted to highlight was different ways that we could test some of these oceanographic hypotheses. So one of the upcoming ways that we might be able to do this is with NASA's Europa Clipper mission. So this just launched in October of this year. And the goal of this mission is to go to Europa and try to assess if this could be a habitable world. So there's a number of different themes that this mission is focusing on. The first one is the ice shell and the ocean. So this is really trying to figure out what the geology is like, what the interior is like, what exchange you have between these different reservoirs of the body. And relating to that exchange, you really care a lot about the composition. So when you look at the surface of Europa, you are struck by the amount of like red material, which we don't actually know what that red material is. There are some constraints, but there's still a lot of open questions. But one of the hints we have is that these are related to endogenic salts. So that suggests another reason why we could have this exchange between the ocean and the icy surface. And in order to understand the surface representation of these exchange mechanisms, you have lots of really fascinating geology where Europa has geologic features that we don't see on any other worlds, like chaos terrains. There's also been suggestions that Europa has plume activity. So we mentioned that Enceladus has these geysers coming out of the South Pole. Europa doesn't have anything that periodic, but there has been suggestions that there are liquid water plumes that might be active on Europa, at least aperiodically as well. So that's another indication that you could have a lot of exchange going on between these worlds. And then the final component that we're thinking about on Clipper is reconnaissance, because going to do this habitability mission from orbit is just the first step in how we want to explore Europa as an ocean world. So the next step would be to eventually send a lander there. So you want to be able to find out what the safest places that you might be able to land a lander and where you would have the most scientific benefit by doing that. So with that kind of broader context, we have 10 investigations that are for this mission. We have a bunch of spectrometers that are used for analyzing the composition. We have a camera to map, and then relevant to the interior and the ocean, we have the gravity investigation, the magnetic field investigation, and plasma. And the one that I'm involved with is an ice penetrating radar, which will then allow you to see into the ice shell and hopefully identify where you could have potential regions of these ice-ocean exchange processes, which then I think relates nicely to interactions between the ocean, the boundary layer, and the overlying ice shell. So we will arrive at the Jupiter system in 2030 and start orbiting, doing flybys of Europa about 50 times starting in 2031. We'll get down to about 25 kilometers from the surface. So one of the things that I think is really exciting to think about in terms of future measurements from Europa Clipper is if we'd be able to identify any ice shell thickness variations that might be present. And one reason that I think this could be really impactful, in addition to constraining the ocean circulation, is that I think it might allow you to decipher whether or not you have tidal heating being predominantly focused in the ice shell or in the rocky mantle, which is a really big debate in the planetary science community. So if you consider a heat flux pattern at the ice-ocean interface from one of Daphne's models that has a radiogenic heat source, and if you look at what the ice shell thickness for a very simplified ice shell model would be if you only include this heterogeneity and heat flux from the ocean, but you don't include any heterogeneous heating in the ice shell, then you get a ice shell thickness pattern that looks like this. And conversely, if you instead have this ocean convection regime with the tidal heating imposed on the seafloor, you get a significantly different pattern of heat flux at the ice-ocean interface, where you instead have more heat flux coming at the poles and less at the equator, conversely. And then in this case, you get a much different signal if you are only considering the heat flux due to the ice shell thickness variations due to the oceanographic heat flux, not necessarily due to any variations in the ice shell. And then if you take all of those, both the ice shell heterogeneity and the ocean heterogeneity, you get this pattern. So you might be able to distinguish between these two scenarios and then I'd infer between radiogenic heating and tidal heating within the mantle as one example. So another idea that's been put forward in a few papers in recent years, that the presence of these zonal jets within the ocean, especially if you have one direction that is much stronger than the others, then you could potentially have the torques associated with those zonal flows lead to a shifting of the location of the ice shell. So that's kind of known as non-synchronous rotation in the planetary geology community. So that might be something that we could detect with Europa Clipper, especially if we compare that to previous, for example, Galileo data. So that's just represented here with one study by Hamish Hay that kind of takes the idea of these zonal flows and calculating the amount of zonal stress that could be imposed on the ice shell. And then the last part that I wanted to highlight here is the possibility for motionally induced magnetic fields. So most of the time when you think about induced magnetic fields for ocean worlds, this is due to the ocean world moving just around the Jovian system with the tilt. So that's what led to the detection of the ocean in the first place. But there's a possibility that if you have a salty, liquid water that is convecting or has flows from other different mechanism, that you could create a small induced magnetic field because it's done in the presence of the strong Jovian magnetic field, or the strong Ganymede dynamo as another possibility. So one way that you can make a very simplistic estimate of what this induced magnetic field strength could be by taking the low magnetic Rossby number approximation that Alban talked about. So here you have dependence on the electrical conductivity, the thickness of the ocean, the flow velocity within the ocean, and then the field strength of the host planet. So then just taking one of the representative models from some of the work that I've done, this is just an example of the radial flow, thinking that that would be the most likely flow direction that you might have a coherent signal that would have a detectable magnetic field signal. So here's just showing you the Rossby number, the velocity of this component in the dimensionless Rossby number units. And then just to get an upper bound on what the velocities could be, you could do a very simplistic redimensionalization of these values, noting that this would be an upper bound in what these flow speeds could be for Europa, Ganymede, and Callisto. And then we can couple this with interior structure models that consider different ice shell thicknesses and different ocean compositions as a way to estimate the electrical conductivity, the ocean thickness, and then use the scaling to make an estimate for what the magnetic field intensity could be. Okay, thanks. So the thing to note for Europa, the most optimistic case would be 20 nanotesla, noting that this is an upper bound, so that seems like it would be a very challenging measurement to do, and you would be wanting to do a better treatment of this if you're going to really try to, I think, use this for observational constraints. I think it's a little bit even more interesting if you consider Ganymede, where instead of relying on the intensity of Jupiter's magnetic field, since Ganymede has its own intrinsic dynamo, the field strength is actually quite a lot higher at Ganymede's ocean than it is in Europa's ocean. So in this case, you could potentially have fields that are more than 300 nanotesla, keeping in mind that these are upper values in terms of the flow speeds. So the reality could be significantly less than this, but I think it does give some motivation to pursue this idea a bit further. Okay, and then to just wrap up, the 3 points that I wanted to leave you all with is that I think planetary oceans are a really great natural laboratory to explore a bunch of different geophysical processes for convection, for mechanical flows, even for electromagnetic MHD effects. And the promise of having all of these different types of ocean worlds is also really exciting, just in terms of the variety and also the fact that we are going to be visiting some of these ocean worlds in the future, that we can test these ideas. And when we go to these ocean worlds, when we make these measurements, they're going to reflect all of these different processes in aggregate. So I think it's really important that we consider all of these aspects collectively so we can understand what the data is telling us. But not many studies have done that because each of these fields is already inherently rich on its own. So it's very easy, as I have done, to just focus on one aspect. So I think moving forward, having those boundaries kind of crossed is a really fruitful direction for us all to go. And then I'll just mention that a lot of this work was reviewed in a recent annual reviews of marine science paper. So if you're interested, you can take a QR code of that paper. So with that, I will say thank you.